In this lesson, we are going to explore the connection between velocity and acceleration. We'll begin by defining these terms and explaining how they are related. Then we will look at some examples to practice identifying the acceleration direction from the changing velocity vectors. By the end of this lesson, you should be able to connect change in velocity to acceleration, identify the acceleration direction for a body in motion, and predict the acceleration from initial and final velocity vectors. Let's start with some definitions. Velocity is the time rate of change of an object's position, and it is a vector quantity defined by its magnitude and direction. In other words, how fast the object is moving and in which direction it is going. In the video on the right, you see a car driving along a highway at constant speed. The left side of the video shows the car's position on a map and the direction that the car is traveling. Notice that the direction of the car changes as it goes around a curve. When the car is traveling along a straight section, the direction stays the same. Acceleration is the time rate of change of the velocity. It is also a vector quantity with both a magnitude and a direction. How fast is the velocity changing, and in what direction is it changing? Since vectors have both magnitude and direction, we usually represent them visually as an arrow. On the map, we see the current direction of the car represented by the red arrow pointing in the direction the car is going. Its length is an indicator of the magnitude of the speed of the car. There are actually three distinct ways the velocity can change. The direction stays constant while the magnitude changes, that is, the car speeds up or slows down while traveling along a straight section of road. The magnitude can stay constant while the direction changes, such as when a car takes a curve at constant speed. Or both the magnitude and the direction can change simultaneously. There are lots of scenarios where this is the case, such as when a roller coaster speeds up going downhill into a curve. Let's take a closer look at the second case, where only the direction is changing, and try to understand how to predict the direction of the acceleration from the change in direction of the velocity vector. In the image on the right, we see an object, such as the car in our driving video, represented by the red dot, about to embark on a journey along the curved path shown. The car's velocity vector at each instant of time is represented by the red arrow. Let's check your understanding. What will the velocity vector of the car look like when it is at the position shown by the X? Will it be A, the same as that shown, B, horizontal to the right, C, vertically down, D, the same direction but longer, or E, 0? Feel free to pause the video to answer this question. If you chose answer B, horizontal to the right, you are correct. The velocity vector is tangent to the position curve at all points. As the car makes its journey, the velocity vector will maintain a constant length because the speed is constant, but the direction of the vector will change as the car navigates the curves. The vector will be tangent to the curve at each point, reflecting the relationship between position and velocity. The velocity is the time derivative of the position curve at each point. Along straight sections of the path, there is no acceleration, since neither the velocity's magnitude nor direction are changing. But what happens when the car rounds the curve? The speed is not changing, but the direction definitely is. If velocity is changing, then there must be an acceleration. We can find the direction of the acceleration by looking at how the direction of the velocity vector changes. Let's watch closely as the velocity direction changes over several time steps. If we want to find the direction of the change in velocity between time steps, we can use tip-to-tail vector addition. We take the initial velocity vector and ask what delta v vector, or change in velocity vector, would get us to the final velocity vector. We add that vector's tail to the tip of our initial vector and follow the path from the start to finish point. Or we go back to our start point and take the shortest path to our final position. That path is our final velocity vector. V initial plus delta v equals v final. What if we take shorter steps in time? In that case, the change in velocity is smaller. It also points in a different direction. Since acceleration is the time rate of change of velocity, we can calculate the acceleration from how the velocity is changing. Over a single time step delta t, the velocity changes by an amount delta v. The average acceleration over that time step is delta v over delta t. If we take the limit of very small steps, delta v and delta t can be replaced by the infinitesimal quantities dv and dt to find the instantaneous acceleration at each point. The instantaneous acceleration is now shown here along with the velocity. For constant speed motion around a curve, the acceleration always points in a direction perpendicular to and towards the center of a circle on the curve at each point. The tighter the curve, the bigger the change in direction of the velocity vector, so the acceleration is larger. Notice what happens to the acceleration vector as the car leaves the curve and heads into the straightaway. The magnitude of the acceleration gets smaller and smaller until the car is moving in a perfectly straight line. Since neither magnitude nor direction are changing, the velocity is constant and the acceleration is zero. What do you think will happen to the acceleration as the car enters the next couple of turns? Check your understanding. What direction will the acceleration point when the car is at the X? Will it be A up, B to the right, C down, D to the left, or E will the acceleration be zero? Feel free to pause the video to answer this question. If you chose answer C, down, you are correct. The acceleration vector points toward the center of the curve in the same direction as the change in velocity. Let's try another one. What direction will the acceleration point when the car is at the new position X? Will it be A up, B to the right, C down, D to the left, or E will the acceleration be zero? Feel free to pause the video to answer this question. If you chose answer A, up, you are correct. The acceleration vector points toward the center of the curve in the same direction as the change in velocity. As we approach and make the turn, the direction begins to change, so the acceleration vector shrinks and grows, always pointing in a direction that is perpendicular to the velocity vector and towards the center of a circle on the curve at each point. At the top of the curve, the acceleration points into the center of the curve, as we saw previously. As the car keeps going, the acceleration vector changes in both magnitude and direction. Notice that the acceleration goes to zero on the straight path again. And as we head into the next turn, the acceleration grows again and is directed upward as we saw previously. When the speed is constant, but the direction is changing, acceleration is perpendicular to the velocity vector and points toward the center of the curve. The magnitude of the acceleration, indicated by the vector's length, depends on how fast the velocity vector is changing. Let's return to our car traveling the winding coastal road. Some of the curves are tighter than others. How do you think the acceleration will compare when navigating a tight curve versus a gradual curve? Let's check your understanding. When a car rounds a tight curve, the acceleration is A greater than, B less than, Or C, the same as the acceleration on a gradual curve at the same speed? Feel free to pause the video to answer this question. If you chose answer A, greater than, you are correct. Why is this the correct answer? Is it because A, the change in velocity direction is greater for the tight curve than the gradual curve? B, the change in velocity direction is smaller for the tight curve than the gradual curve? C, the change in velocity direction is the same for both curves? Or D, the time step is the same for both curves? Feel free to pause the video to answer this question. If you chose answer A, the change in velocity direction is greater for the tight curve than the gradual curve, you are correct. In summary, velocity and acceleration are vectors with both magnitude and direction. When the magnitude of velocity is held constant, but the direction changes, the acceleration can be found from tip-to-tail vector addition. Acceleration is in the direction of the change in velocity. The bigger the change in the velocity direction, the greater the acceleration. Thanks for listening. I hope you enjoyed this video.